All right, good morning, everyone. And I think we're really missing like maybe two people right now, but we'll get started. Happy Friday. Uh, Today, I wanted to really talk to you guys about the homework, and I want to go over every single one of you guys on the questions here with you guys so that you guys understand how to do these. And that is pretty much going to be it in terms of content wise of how much you guys are going to be um, learning. Starting next week, I know it's going to be like crazy with the rotating schedule, which I have never done before. So I still have to kind of figure out my way as to how this is going to work out. Next Tuesday is the day that we're going to meet up. And Monday, we're not meeting up because it's going to be a day two, I believe. So Tuesday, we meet. Wednesday, which is going to be day four. And then Thursday, which is day one, and then Friday we do not meet again. So it's going to be three times in that given week. Now, regardless of what happens, I'm going to try to figure out a way that is easiest for all of us to take an assessment that day. Whether it be Wednesday or Thursday, depends on which day is kind of feasible for all of us here. But I believe that every single one of those days, well, actually, day one seems to be the most appropriate. So I'm gonna put it on the note and say that everyone's gonna be taking like on Thursday, we're gonna be taking a like a like a test on all of this. So that includes exponential functions, equations, and logarithms, word problems, properties of logarithms, value of e, natural log, and all that good stuff. Okay, so it's gonna be very extensive, and period three grades will all be done pretty much by then. And yeah, so that's pretty much it. So in terms of like how to prepare for this goes, I am going to make sure that the next 2 days in which what we're going to be meeting up, Tuesday and Wednesday, I'm going to provide you with a study guide, and I'm going to provide you with the answers and all that good stuff here. And so during, at least for this, over this weekend, just take a break and relax a little bit. And once we come back to school, we'll get down to business. Okay. If you guys want to get a little head start on the study guide, I will post it over by the end of today, just so that if some of you guys want to get head started and just want to work on this, you totally can. But remember, I want to give you guys some time during the class also to work on it, and you guys can just ask me questions if you guys ever feel the need to do so. Okay. All right. So number one, Mr. Jenkins needs $300,000 to retire comfortably in 25 years. If he invests $35,000, what is the rate of growth? Okay. So this type of word problem, like we haven't really done before together in class, and I admit that it's been a long time. So here's what I need you guys to do. You are still going to use A is equal to principal times e to the power of RT. And the amount of money that you want to end up getting is about $300,000. And that is equal to the principal, 35,000. So you're simply going to plug everything in. E to the power of R, which is something that you do not know. But the time here is going to be 25. So I'm going to write times 25 like this. Okay. Now, some of the students kind of actually asked me, like, they really don't know how to do a question like number one, for example. And so here's what you have to do. First, you have to divide both sides to solve for this equation by 35,000. So you can get E by itself, right? So here I get 300,000 divided by 35,000, and I get 60 over 7, which comes down to 8.57143 equals e to the power of 25r. Now, remember, if you're ever asked to solve for questions like these, you're gonna have to take logarithms on both sides, or you can take, convert this into what we call a logarithmic form. So converting this into a logarithmic form would state that it will be a log base e, because that's what it's being raised to the power by, of the output of 8.57143 is equal to 25R. So remember, be fluent, be flexible in how you can translate between a exponential form to a logarithmic form. Very important that you know how to do that. So then that's just simply a natural log of 8.57143. And so what you're going to get is 2.14843 equals 25R. Divide that by 25 because obviously I want to get R by itself. So R is going to be 0.085937, which comes it down to the 8.59% growth. So with an annual interest rate of 8.59%, by a continuous function, which means you're doing this infinite amount of time, a continuous function, compound interest over the course of 25 years, that's going to be $300,000. Okay. All right. So part B says if the stock market has typically averaged a return of 9.4%, how much money would Mr. Jenkins accumulate in 25 years if he deposited $35,000? Now this one here, this is the one he invested, and this is, I guess, they're using they're talking about stock market. So I guess part A is investing in something totally different. So you do the same thing, but in this case, this is something you're looking for is A. So 35,000 times E raised to the power of 0.094. Please remember how to convert the percentage into decimals as well. So I'm just going to type that in. 35,000 times E to the power of 0.094 times 25. About $366,995 compared to $300,000 from previous investments. So I guess stock market does obviously give you a lot higher output here. Any questions about number one that you guys have? All right, number two. So when Angelina was born, her grandparents deposited $3,000 into a savings account, paying 4% interest, compounded continuously. Remember, that's the word that they're looking for. There are no deposits or withdrawals from the account. What would the balance be after 10 years? Can I have a volunteer from the class? Tell me what the answer is to part A here.
Is it $4,475.47?
$4,475.47. Is that right, Kate?
I think so, yeah.
Yep. All right, there we go. So again, it's 3,000 e to the power of 0.04 times 10. And yeah, you're right. Just plug that in, and there we go. How long will it take the balance to reach at least $10,000? So here we taking 4% interest about 10 years, and it's nowhere close of getting 10,000. So obviously you might want to think about the answer being like, I don't know, 30, 40, 50 years. So 10,000 is equal to 3,000 e to the power of 0.04 times t. This is the equation you want to set up for. Again, I'm going to ask the volunteer to somebody help me out with this one.
I got
30.
Oh, my bad, Eddie.
Oh, no, yeah, so.
Yep, any one of you guys.
Yeah, I got 30.01 years.
0.01 years like this.
Yeah.
Okay, so I did a natural log of 10,000 over 3,000. I'm skipping a lot of steps, by the way. Is equal to 0.04 t. And so when you do that, divide by 0.04, I get time is equal to about 30.0993 years. Maybe you had a little rounding error, but the exact decimal value that I'm going to end up getting is about that. So how long will it take the balance to reach at least 10,000? Well, it didn't say it really rounds up or rounds down. So if I wanted to get an exact time, I would say 30.0993. But if they want to round it up to the nearest integer, it has to be 31 years because 30 years is not going to cut it. It's not going to give you at least $10,000. If her grandparents wanted Angelina to have $10,000 after 18 years at the same interest rate, how much would they need to invest? Okay, so $10,000, they need to invest the principal amount of some kind. E, at the same interest rate, which is 0.04% at the end of 18 years. So we're looking for principal. This one might be a little bit easier to do because all you got to do is calculate that and just divide it onto the other side. So I think, Eddie, you were the one who answered my question last time. So there was a little overlap with the voices. So can I have the other person, I didn't catch your name, to tell me the answer, please?
Yeah, I got $4,867.52.
52 cents. All right, so 10,000 divided by E 0.04 times 18. And absolutely that's the case. So guys, every single one of these questions, you guys are just going to use your calculator. Okay, just have your calculator by your side and just knock out all these problems out. Population, Michigan's population was 2000 was 9.9 million people and increased by 0.28% each year. Use the formula that to write a function of Michigan's population Y after T years. Okay, so assuming 2000 is year 0. So population here, we are going to leave it. Population 2000 was 9.9, so that's the initial amount. And since T is the amount of time since 2000, we can just leave it as E to the power of 0.28% is 0.0, I believe twice. So that will be 0.0028 times T. So that will be the equation that you would be using here. So in 2007, the population of Georgia was 9.36 million people. In 2000, it was 8.18 million people. Use the formula to determine the value of K, Georgia's relative rate of growth. So here you're going to be doing the same thing as what you've been doing for question number 3, I guess. So 9.36 million people, E to the raised to the power of K. And I say that, the time here is going to be 0 here. So that means that your initial amounts was, I'm sorry, I should have used the 2000 because this was the earlier one. So in 2000, it was 8.18 million people, E to the power of the rate in which what we do not know, but the time is going to be 7, and you're going to plug in 9.36 million people here. Okay, once again, if you guys are asked to solve for something like this, please divide both sides by your initial amount, which kind of tells you how much rate is being multiplied by from the original, 9.36 divided by 8.18. And then you get 1.14425 is equal to E to the power of 7K. You take the natural log of 1.14425, rate, divide that by 7, and you get the rate to be 0.01925, which comes out to be about 1.925% increase. When will Georgia's population reach 10 million people? Now, I hope some of you guys are actually got this answer, 1.925%. If you didn't, here's the work for it. Again, part B is a lot easier. All you got to do is plug into the formula that says Y is equal to initial amount, which is 8.18. I'm still going to be using this because that tells you if I solve for the time. Actually 10 million people, I have to plug in 10 right here. It's going to be E to the power of 0.01925 times T. And this T, if it becomes like 10, 20, 40, I have to just add it to 2000, which makes my math a lot easier to do. So I'm going to solve it by dividing both sides by 8.18 on both sides. And then 10 divided by 8.18, take the natural log of that, divide that by 0.01925. I get time to be about 10.436, which means 2010. Actually, the year, if we're going to actually talk about the year, then I guess we have to talk about it in terms of like 2011. That's actually when it's going to reach about more than 10 million people. But to be exact, it's about 10.436 years after 2000.
Mr.
Actually,
Kim, I
I
have
like
a
that answer
question.
better. I'm sorry, what's up?
I have a question.
What's up?
So for the one about Michigan, wouldn't it be 0.0128 because it's increasing?
Oh, are you talking about the value that has to be up here?
Yeah.
So for continuous functions, a is equal to PERT, and simple interest, compound interest would be P times 1 plus R over N raised to the power NT. So there's that 1 coming from. That's what you're talking about right here. The rate itself is always the decimal value of the percentage of the increase or decrease by. So if I tell you just straight up R, that means that you're actually just using 0.0028 and no more 1 pluses.
Oh,
The
okay.
one-
Thank you.
Yep, the 1 plus those portions has been taken care of by E. E is the value that you get when you do this, okay? And you do that infinite amount of times when n is approaching to infinity. So the 1 plus portion has been taken care of by E, if that makes sense.
Yeah, I got it. Thank you.
Perfect. All right, so the more
I have a question,
appropriate.
Mr. Kim.
I'm sorry, what's up?
I have a question.
What's up?
So for like A and B for number 4, like how
Yeah.
did you do that stuff? Like you divided, but then like how did you get like the E? Like you did like log E or something? Like I don't know.
Yeah.
I'm
Oh,
confused on
sure.
that.
So first you understand that we have to divide away the initial value, right?
Yeah.
Okay, so the next thing that you get is you get this 1.14425 is what you get after you divide that in your calculator. All I did from here is that I translated that into what we call a logarithmic expression, or better yet, what I like to is take both sides by log of whatever the base it says. So for example, the base refers to the number or a variable that's getting increased or getting raised to the power by. So here it's E. If you take log base E on both sides of the equation like this, then what happens is by using the power rule, the 7K from this actually becomes, to the front, like it becomes a coefficient. And then the log base E of E, that's one of those properties too, that when the base number and the number that it's taking logarithm of is the same thing, they actually completely cancel each other out. So basically what you end up getting is log base E of 1.14425 is equal to 7K. This is same thing as saying natural log, or you can just simply do log base E if you want to. And if you do that, I think I have it somewhere here. So natural log of 1.14425, I got 0.134749 is equal to 7K. And I simply have to divide that by 7 on both sides of the equation so that I end up with this K value right here.
Okay, so you do this when we don't have like R or T or like K, like the ones on the
You always take log on both sides, or you always do the stuff that you have just seen right here whenever you're asked to solve for a variable that's in the exponent, because you cannot solve for the variable in the exponent. Remember when we took this way back in the past, the very first time I showed you guys logarithms, I gave you questions like this. How do you solve for questions like that? I cannot translate 17 into a form of power of 3. So I asked you guys, okay, look, the equivalent logarithmic form would be log base 3 of 17 is equal to V. Now I told you that, but the main idea that really came from is that if you're trying to solve this algebraically, is that you're taking basically what we call a log base 3 on both sides of the equation. And then the log base 3 and the 3 will cancel each other out like completely, like these two will cancel each other out. So V is equal to log base 3 of 17. Either way, it's going to give you the same result.
Okay, thank you.
Yep. All right, so going back, answer for part B should be like T is about 10.436 years after 2000. Obviously, it will be 2010 and some change, maybe 2010 and some months. But that will be a much more appropriate answer because it doesn't say when we'll reach. Well, I guess you can say 2011, but it doesn't give you exactly 10 million people. All right, so we have one more page to go with bacteria. So bacteria is usually the type of context that they give you because they continuously tend to grow in a natural world sense. They are growing at a rate of about 4.32%, given by this factor right here. Determine how long it will take before the numbers of cells of this bacterium to triple. All right, so here's a question, Jack. This is the perfect question for us to practice with. And so if I want the bacterium to triple from the initial value of 50, what's the Y value that it's trying to approach to?
150.
150 is equal to 50 E 0.0432 T. Obviously, the first step is to divide by 50, and this actually becomes 3 is equal to E 0.0432 T. Okay, so remember, I am looking for the value of T here because E is just a number. This is 0.0432, it's a number. I'm looking for the value of T, but you see how it's in the exponent, right?
Yeah.
So then I want to bring it down to the same level as the coefficient so we can actually tend to solve this. So what am I going to do to both sides of the equation? Or better yet, can you tell me the equivalent logarithmic expression of this exponential equation?
So would it be log base E of 3 and then equal to 0.0432 T, sorry.
That is absolutely correct. That is what that's it basically. So here what I'm going to do is I am going to take this and say, okay, so they want me to do natural log of 3. Natural log of 3, and I divide that by 0.0432, and I get time to be 25.4308. So determine how long will it take before the numbers of cells of this bacterium to triple. Usually the T is in years, so it will be 2 years after. 25.4308 years after, it's going to triple its numbers.
I have a question. So like
Question?
when we got like a decimal, like do you want us to like the 4 decimal places?
No, I just wrote down 4 decimal places because that's what it says in my calculator. In the test or assignments, I will tell you round to the nearest 1,000, round to the nearest 100. If I don't, then during the test, I'll specifically tell you what you need to do. All right, so part B. A second type of bacteria is growing exponentially according to the model of that, where T is time in minutes. There are 1,000 cells initially and 1,650 cells after 40 minutes. So here, time is already specified. It's in minutes. It's not in time. It's not in. I mean, it's not in years. So I'm going to plug in everything that's according to it. 1,650 equals 1,000 times A, e to the power of K T, which is 40 minutes. Now, the only problem here that I see is that second type is growing exponentially according to the model, and there's no value for A here. So it's going to be impossible for us to solve this without having a secondary equation, or better yet, if there was a typo to this, then that's the only thing I'm going to say here. There's no way other than to solve this by just getting rid of this A, because I think what they meant, A was the initial value, but it's already initially plugged in as 1,000, or they should have just deleted this in the first place, because then the students will plug in 1,000 cells into A and 1,650 into Y and then solve it. If you don't have the answer for part B, that's fine. And this was completely a typo. It's their fault here. So we're going to do 1,650 divided by 1,000 and then do the same thing. Take the natural log of the answer, divide by 40. So the decimal value here, the K value or the rate, because that's the only thing that's really left over, is 0.012519, 1.2519% increase. That's the annual interest rate. Yeah, sorry about part B, guys. That was something that it wasn't, you can't really take care of that. All right, 6, the half-life. Now, half-life is basically how long it takes for a substance to decay by or be reduced by about 1/2 or so. So that's what's called what the half-life is. So the half-life of a radioactive substance is the time that it takes for half of the atoms of the substance to disintegrate. I think this is what I talked about when I'm talking about chemistry. If finding the half-life of things and so forth. So the half-life of carbon-14 is 5,730 years. Now, what that means is the substance in, let's say, in bones and structures that we find in carbon date, well, that's why it's called carbon dating, right? If we can find out how much of the radioactive substance has been remained after the course of time, we can figure out how long this bones or fossils has been around for many, many years. To determine the value of K in the equation of decay for carbon-14. Now, this is a naturally decaying substances. We're using a natural logarithm. That's why the value of E is so important, because it explains how many things just happens in a natural world. So we're using the continuous function, A equals P E to the power of RT. The rate is something that we do not know. They use value of K for some reason, but I like to use the value R because it just makes more sense, R for rate. Carbon-14 and the half-life is 5,730. Now, what does this mean? Now, I know that it's missing a lot of components here, so I'm going to help you out with this. Let's say that the initial amount of this radioactive substance in the beginning was 100, okay? There's 100 radioactive substance in the carbon. After 5,730 years, you know what happens? It becomes about 50. Half of those radioactive substance has been disintegrated. So what I'm going to do is I'm going to say, okay, so the outcome is 50 with the initial value of being 100, E to the power of R after 5,730 years. Now, it doesn't matter what numbers that you decide to use for these two. It doesn't. You can use 10,000 and then this is going to become 5,000, but at the end, you're still going to be dividing away that initial value with the outcome. So what you're really doing is taking 1/2 is equal to E to the power of R 5,730 power, and then you're solving it accordingly. This number will not change. That number will indicate the half-life. Now, I really didn't teach you about half-life, but this question kind of summarized it. I don't think it's really worth necessarily going and talking to you guys about what half-life is. Half-life is simply how long it takes for the substance to decay by half. And then you want to find out the rate in which how fast this disintegrate. I can't really pronounce that word out for some reason. So I'm going to do the same thing as I've been doing before. And if you guys haven't done this, please follow along with me. We're going to be taking the natural log. Okay, so because I want to cancel out this E here, we're going to take natural log on both sides. Natural log of 1/2 equals 5,730 R. So I do that in the calculator. Ooh, I get a negative number. So then here I get 5,730. And guess what? The R becomes negative 0.000121, or better yet, that's negative 0.00. I'm sorry, that's not it. Trying to find out the percentage value for you guys. So I'm going to move this right twice. So it's 0.0121%. Oh. So that's how fast it disintegrates. Now, why the negative number, you might ask? Well, and I really haven't given you an example of a negative number because we're talking about something that's decaying, right? This is disintegrating. The radioactive substances are decreasing in the amount. So there we go. So it's about 0.0121%.
It's okay. I'm sorry. I have another question.
What's up? Yes, please.
So like, I know how we like went over like 2 questions back, like the log base E and like it cancels out and stuff. So you did natural log here. Is that like the same thing or?
Natural log is the same thing as log base E, by the way.
Okay. Thank you.
Yep, natural log is that. All right, so part B, a paleontologist examining the bones of a prehistoric animal estimates that they contain 2% as much carbon-14 as they would have contained when the animal was alive. So how long ago did the animal live? Okay, first of all, let me get my head around this. A paleontologist examining the bones of a prehistoric animal estimates that they contain 2% as much carbon-14 as they would have contained when the animal was alive. How long ago did the animal live? So here we are looking for time. Okay, how long ago did the animal live here? And if we're talking about the rate at which how fast this is disintegrating, we're using the same ratio, I believe, from the above answer here. Okay, because we're talking about the carbon-14 of decay rate. So the rate here is going to be negative 0.000121. So part A is really crucial to solving all these other questions. And time is something that we do not know. A is equal to PERT. So if we're talking about, let's say, for example, when the animal was alive, 2% as much carbon-14 as they would have contained when the animal was alive. So if the animal was alive and I had, let's say, about 100, the radioactive substance, let's say, that is the initial amount, let's say. The initial amount was 100. Now, can I make up a random number? Well, absolutely, because in the end, you're going to divide away to the other side of A. And the bones of a prehistoric animal, they contain only about 2% as much carbon-14. So 2% of 100 is actually 2. So this is actually telling you that the first answer was a half-life question where it allows you to calculate the value of R. Whereas this one, you're dating way back in the past and going, oh, well, now I only have 2% of carbon left over compared to 100. And so E at negative 0.000, I believe it was 121, and times T. So let's figure this out here. It's going to go way back into the past. This was about this bone that was discovered was about 5,730 years in the past. This one's going to take way more than that. So 0.02, because I'm going to divide both sides by 100. 0.02 is equal to e to the power of negative 0.000121 times t. And let the calculator do the work. Natural log of 0.02 divide by negative 0.000121. Yeah. So natural log of 0.02 equals negative 0.000121 t. And time here is actually going to be about 330.8 years. So what we're talking about is this radioactive substance that was discovered, or carbon amount that was discovered in these bones. It's only 2% remaining. It's like, how much fuel is left over after the course of time. And you only have 2% left over. That means this bone is really, really old. This bone is about 32,000 years, prehistorically dating back. If a prior research points to an animal being around 20,000 years old, how much carbon-14 should be in the animal? So this one is kind of like saying, okay, this was only estimated to be about 20,000. How much carbon-14 should have been in the animal? That's what it's talking about. So A is what we're looking for. Principal, let's say, is about, I don't know, let's say it's going to be 100, okay, because that's the original amount that we used. E to the power of R, 0.000121 times T, which is about 20,000. So if we're to do this, okay, and if we just multiply it, okay, because everything is just going to be a number. So I'm going to take 100 times value of E. Remember, this number really doesn't matter, but I'm trying to keep it consistent with you guys. I know I made up a principal value, but either way, it's not really going to make a big difference. You can make it 1,000, you can make it 10,000. It's still going to give you the same answer. So I'm going to multiply that by 20,000 here. And what I get here is that I get about 8.89216. Guys, that means that original 100 amount now becomes only about 8.89. So that comes out to be about 8.89% of carbon left over. What does that mean? Well, it means that before we took about only 2%. That's because that was 2 out of 100. Okay, we only had 2. This one gives me 8.89, dating back 20,000. So how much carbon should have been there? Well, it should have been about 8.89% carbon should have been left over. Because we don't know how much, we can't say, the actual amount of carbon. We got to say in terms of percentage of the original. All right, 2 more questions to go. I know that this question was really elaborate, but if you kind of go through these with me, I feel like it's gonna help you out in terms of understanding how to solve for very complicated word problems such as this. A specimen that originally contained 42 that's gonna be what is it called? That's mu. I forgot what that was.
Is it nano?
Nano isn't gonna be. Oh, this is gonna be a microgram. I know that this is gonna be 10 to the -6. Oh my goodness, I probably should not have done this here. Yeah, so this is going to be a microgram. It's been a while since I've seen this one. Nanograms is going to be a lot more. I think that's 10 to the -9. Now contains 8. Okay, so the unit really doesn't matter because how old is the fossil? That's what it's asking. So ignoring the units here, a specimen that originally contained 42 now contains 8. How old is the fossil? Okay, so e to the power of the rate, which I'm going to still use the same thing, raised to the power of t. All right, so 8 divided by 42. We're going to take natural log of that. Then divide it by -0.000121. And you get about time to be 13,704.4 years. Okay, so I'm going to show you the work for this. So for this one, you obviously have to divide by 42 on both sides of the equation. 8 over 42 is equal to -0.000121 t. And then you take natural log on both sides of the equation to get rid of e here. So natural log, natural log of 8 over 42 is equal to -0.000121 t. So the last step to do is just really get rid of this, the coefficient by dividing this away. And so you get, if you compute this into the calculator, you should get t is equal to 13,704.4. Yeah, I was kind of getting scared with the units here, but the units have no significance matter. It's called micrograms, by the way. Okay, last question before we end the session for today. A woolly mammoth specimen was thought to be about 12,000 years old. How much carbon-14 should be in the animal? Okay, so here's what's happening basically. So we don't know what A is and we don't know what P is. Like we don't know what the principal amount of carbon left and the actual amount that the carbon is being left over after 12,000 years. But what we do know is E. We know the rate from part A, and we also know the time. Those two are the only things that we know. So if you were to actually do this component right there, that's the only thing we could possibly do. And believe it or not, it actually tells you the answer. So I'm going to take that and then multiply those together. And I get A is equal to the principal times what we call 0.234102. Okay, I know that I'm writing all the decimal values there, but okay. So what does that mean? How much carbon-14 should be in the animal? Well, it turns out to be that original amount and times 23%, 23.4102% gives you the actual amount. So we can say about 23.4102% is left over. Original times this amount gives you the actual amount. So the actual amount is about 23% of the original. So that's what you say. So that's what carbon dating is. How we can kind of, not accurately, but approximately measure how long ago that these fossils, that these bones, how old they are when they were alive, basically. Okay. Woo. When question 6, archaeology, that was a very extensive question indeed. And I know that maybe some of you guys did not really give this a try because, yeah, it is a very complicated problem. So I still put it there just for, the sake of, practicing. This really enters the realm of science rather than really mathematics. But, a lot of science is mathematics here, as you can see. And yeah, this is basically how I I hope you guys understood how half-life works, how carbon dating works. This is just a very simple questions, but obviously carbon dating in its detail is much more complicated than that. But you get the sense of how this is measured. Okay. I'm gonna upload this video on YouTube so that my group A kids can see it. Now, no longer are we gonna see group A and B, rather A, B, B, C, and AC. So I don't know who I'm gonna see and who I'm not gonna see on Tuesday. I think Tuesday will be BC day. I'm not sure if that's exactly correct. Just let me verify that real quick. Oh no, April 20th will be an AB day. So for those of you who belong in group A and group B, I'll see you guys in class. For those of you who are remote, obviously I'll see you on virtually, and also the group C kids. Remember, next week, Thursday, I'm pushing for the test. All right, so this is pretty much it to the extent of how far I'm gonna take today's lesson. I'm not gonna give you guys any homework, but remember, I'm gonna give you guys a study guide in advance, which you will also receive from me next week anyhow. And if you guys wanna get a little head start on that, you may do so. You have no homework from me over the weekend. Just relax, take care of yourself. And I'll see you guys on Tuesday. Everybody.
Thank you, Mr. Kim.
Thanks, Mr.
Thank
Kim.
you.
Thank you. Have a nice day.